Hello, today we're going to do a video on entropy. I'm going to start with a history background, and I'm going to do a quick explanation with metaphors.
Entropy is a fundamental concept in thermodynamics that helps explain how energy moves and why natural processes occur in a specific direction. In this presentation, I'll focus on the background of entropy and on the mathematical formulas that define it, which will set the foundation for the examples discussed later. To understand entropy, it's important to realize that energy conservation alone is not enough to explain real processes. Even though energy is conserved, not all processes are possible. Entropy is introduced to explain why some processes naturally occur while others do not. Entropy can be defined as a thermodynamics quantity that measures how energy is dispersed and how many ways energy can be distributed within a system. It also explains irreversibility, meaning why natural processes tend to happen in one direction. Entropy plays a central role in thermodynamics, particularly in explaining spontaneous heat flow and the limits of energy conversion. Entropy matters because it determines the direction of natural processes. While the first law of thermodynamics tells us that energy is conserved, it does not tell us whether a process can actually occur. Entropy fills this gap by introducing irreversibility. It also explains why engines and refrigerators cannot be perfectly efficient, since some energy always becomes more dispersed and less useful. More broadly, entropy connects thermodynamics to fields of statistical mechanics and information theory. The concept of entropy was introduced in the mid-19th century by Rudolf Clausius while studying heat engines. He noticed that energy conservation alone could not explain irreversible processes, so he introduced entropy and formulated the second law of thermodynamics. The word entropy comes from Greek, meaning transformation. Later, Ludwig Boltzmann gave entropy a microscopic interpretation, linking it to probability in microscopic states. In classical thermodynamics, entropy is defined using heat transfer in reversible processes. For an infinitesimal reversible process, entropy change is defined as delta S equals the reversible heat transfer divided by temperature. For a finite process, entropy change is found by integrating this expression. Even though real processes are irreversible, entropy change can still be calculated by imagining a reversible path between the same initial and final states. One key property of entropy is that it is a state function. This means entropy depends only on the initial and final state of a system, not on the path taken. This is different from heat and work, which depend on the process itself. Because entropy is a state function, it can be tabulated and used efficiently in thermodynamics calculation. The second law of thermodynamics states that the total entropy of an isolated system can never decrease. Mathematically, this is written as delta S greater than or equal to 0. This law explains irreversibility, why spontaneous processes occur naturally, and why perpetual motion machines are impossible. It also defines the general direction of physical processes. Now that the background concepts are established, we can focus on the key entropy formulas that are commonly used in thermodynamics problems. For real processes, the general entropy change includes both heat transfer and entropy generation. For liquids and solid, entropy changes can be approximated using the incompressible assumption, leading to expressions involving temperature only. For ideal gases, entropy change can be written using temperature and volume or temperature and pressure, depending on which variables are more convenient. An isentropic process is one where entropy remains constant, meaning the process is both reversible and adiabatic. For ideal gases, this leads to important isentropic relations between temperature, pressure, and volume. These relations are widely used in the analysis of devices such as turbines, compressors, and nozzles.
Entropy is a property of a system that gauge how much spread out or disorganized a system is. Example, if you have a high entropy, you're going to have a system that is highly disorganized or chaotic. And if you have low entropy, you have an organized system. It's a concept that is used in physics and probabilities. I'm going to give you a small example. This is a cup of hot tea. It's low entropy, really organized, and all concentrated in one place. Entropy always go with time, so as you expect, time go by, and usually what would happen is that the warmth in my tea would go around the room and they would equilibrate in temperature. That's high entropy. That's disorder, and that's always how things would spread out. And since time that pass always means more chaos and more entropy, that's the reason why every time I take my earphone to listen to some music, they're tangled. because there's a billion ways for them to be tangled, but there's only one way for them to be untangled. So I guess probability wins on that one. Now I'm just going to talk about the second law of thermodynamics that states that entropy is always going to go higher as time goes by. I can give you an example. This is my room, it's pretty clean. But if I live in this room and I don't do any effort, things are going to get messier. Like my roommate's room.
Hey, yeah.
Like this.
Oof.
Entropy always tends to go higher, and things always will get messier. Thank you for listening to our video.